Hello and welcome to Physics 100 at Mount San Jacinto College. I am Professor Lee and I'm going to be your professor for this semester. Today we're not going to go over a ton of material. We just have about 9 slides to go through, uh, but it will give you a taste of what this class is going to be like and just a general introduction to physics. If you haven't taken it before, which given that that's a conceptual class, there's a very good chance that you have not. So, what I am going to do is I am going to read from the book, which I will post again and post a link at the bottom of this video. And I am going to paraphrase it. So I'm not going to go through everything and I'm not going to agree completely on everything that's been said, but I am going to just go through the important parts, make sure that you're able to do the homework and make sure that you get the important details. This is also important because we are unable to uh, do every single thing that's in the book because this does not require algebra. It's going to be completely uh, conceptually based. So there might be formulas such as FA equals MA or E equals MC squared that you might see that, and you might find uh, interest in that, but there isn't going to be any uh, algebra that you have to do, no rearranging the variables for this class. So with that said, I'm going to start on with chapter 1, what is physics? So, okay, there we go. So physics comes from the word physis, I believe, which is the Greek word for nature, and the original name for it is natural philosophy. So this is both the initial name for physics and for science in general, as far as I know. So physics can be seen as kind of the most pure science, uh, where uh, we try to answer questions about the most fundamental forces and laws in the universe. Uh, but uh, this physics is what we're going to do to be able to solve for that. And then as you get more complicated, as you find interesting things from physics, what happens is that it eventually morphs into its own field of study. So chemistry can be seen as applied quantum mechanics, which is something from modern physics, and biology as applied chemistry. But physics is the underpinning of all science, I will say, even if it does make me sound a little conceited. Uh, but when the area of study becomes too complicated, it becomes its own field, such as chemistry, physics to chemistry, or chemistry to biology. But the underpinnings of all of these sciences is the science of physics. So we're going to break this up into classical and modern physics. So some of the subfields of classical physics that you're going to see, because it is such a broad field and everything comes from it, uh, you're going to see a lot of different sub fields inside of physics that haven't become quite enough to become their own, complicated enough to become their own field, but are complicated and unique in their own ways. So when you talk about Newton, uh, so Newton or Galileo, you're talking about kinematics usually, which is the study of motion. So how forces, which are pushes and pulls from own objects, are going to cause a motion, what the relationship is between this motion and the force that's applied. Gravitation is also something that Newton found interesting that I didn't actually put on here. As well as that, he also studied optics, which is the study of light, and that has led to a surprising amount of information about electromagnetism and general relativity eventually. So you start out with the basic idea of motion, and then Newton, who came up with the three laws of motion, studied optics, and then from optics you got electrodynamics, and from electrodynamics you were able to come up with general relativity, or Albert Einstein was able to come up with that. There's also another major field called thermodynamics, which is the study of heat and temperature, which is going to be important because it gives rise to quantum mechanics, and quantum mechanics is how we explain everything that we see in chemistry. So these are some of the subfields of classical physics. Basically, what happened was that this was between, I think, the 1600s and the early 20th century. And in the early 20th century, particularly in 1905, there were several papers published which just completely recreated what we saw and what we understood from physics. So that the main fields that came out of that were relativity and quantum mechanics, and those are classified as modern physics. And there are going to be a few reasons why we didn't notice these properties beforehand in classical mechanics. That's going to be that only became feasible as technology got more progressive. And as well as that, there is just also the fact that in 1905, Albert Einstein, while working as a patent clerk, published 5 different papers, which completely changed the outlook of physics and the field of physics in 5 different ways, in what's called his miracle year. And because of this, through the 20th century, physics just expanded massively. And at the end of the 20th century, Time magazine named Albert Einstein as the person of the century for this massive expansion, which shaped both our understanding of the natural world and the technologies that we use to interact with it. So the first major subfield of modern physics is called relativity, which comes out of electrodynamics, which comes out of optics. It's the study of electricity, magnetism, and light. And basically what was found was that the speed of light is constant relative to the observer, regardless of how fast the observer was going. So this is interesting because as you sit, if you go off in a spaceship relative to Earth, going at 95% of the speed of light, the speed of light to you is still going to look like it's traveling the same amount of speed. And in order for that to happen, because speed is length over time, length and time get warped and aren't constant as you travel at different speeds. So this is something that can really only be seen when you're talking about high speeds or you're talking about high gravity, because it turns out that this space and time, or what we call space-time, is also warped by the presence of large gravitational fields. So that is why we didn't notice it in classical mechanics, and that's why classical mechanics breaks down at high speeds or high gravitational fields. And it's also necessary to make observations about fast things and things in high gravitational field, such as particle accelerators and the GPS that you see, because the GPS that you use, because the gravity is different in outer space than near the Earth, it has to make tiny changes and calculations based on the warping of space-time, based on this change in, or the warping on space-time based on this change in length and time in high gravitational fields. As you go to a lower gravitational field, you're going to have different length period distances and time periods for the same events. So when that happens, it's going to throw off the data that the GPS is able to get from sending light waves between your car and the satellite in space. So we have to correct for that in order to get GPSs to work well. So quantum mechanics is the other major thing that came up in the 20th century, again, largely due to Einstein. It's instead of being derived from electrodynamics, it's derived from thermodynamics. And the main idea is that any object can be described both as a particle, which is like a hard, this is what it is, there's no wiggle room situation, and as a wave, which is showing that there's some probability that you can like be spread out a little bit, like ripples on the pond from the center position. You have some probability of being farther away from the center position or closer to the center position, or a myriad of other things. This is vast oversimplification, but we're going to get into the details of it later in the semester. And what this, the most interesting fact about this, and the thing that, the reason it's called quantum mechanics, is that quantum means that there's a countable number of things. So you have one thing, two things, three things. That's counting quanta. And quantum mechanics says that there are only certain energies or other types of states that a particle slash wave slash object, what we were talking about, is allowed to be in. So because there are only certain allowed energies, then that makes it so that, or energies and states, that makes it so that when you talk about chemistry, you talk about these only certain allowed states, and that's why basically atoms and molecules have predictable properties instead of just being a mess and blurring all over everywhere. So it's necessary to understand chemistry, and it's also necessary to understand quantum or complex electronics, which are like most notably the transistor, which is what basically all of our computers are based on in the past 50, or no, it's been like 70 or 80 years now. But it wasn't noticed very until recently, because it's mostly only noticeable with very small objects. So with classical mechanics, you can describe larger objects like a rock or a car. But when you get down to the size of a proton or an atom, then you're going to have to talk about quantum mechanics. So that is a brief overview of what the field of physics has been doing for the past 600, 700 years. And the way, the reason that we can talk about it and the reason that physics is able to make these predictions and make these new technologies is because it is the fundamental science, and that means that follows the scientific method. So a scientist makes an observation and comes up with a hypothesis, which is an educated guess about why something is occurring. The hypothesis can then be tested by an experiment, which is either going to say that the experiment is right, or say that the hypothesis is right or wrong, or somewhat right or somewhat wrong. And once this experiment is done, it allows us to make a new hypothesis. And then if the hypothesis is variably tested by experiment, then it yields a theory, which is like the theory of gravity. It's the theory of gravity, or a scientific law, which is like Newton's 3 laws of motion, or Einstein's law of, or Einstein, I guess, is a theory of relativity because it hasn't been completely accepted in the same way that Newton's laws have. But a scientific law is a theory held to be universal, and the difference between a theory and a hypothesis is that a theory comes about after the hypothesis has been tested. So that is the general scientific method. We also need to be aware that everything that we do is just a model. So it's just made up to describe science under certain circumstances, and physics tries its hardest to build laws instead of models. But in the end, what we are building is just different models for different circumstances that we're able to see. So the reason, say, that relativity is a theory and quantum mechanics is a theory rather than a law is not that they haven't been tested and found to be very successful at predicting outcomes. It's that quantum mechanics and relativity are kind of incompatible with each other. So relativity describes really big objects, and quantum mechanics describes really small objects. And when you do the math for them, they don't really agree as well as they could. So that's why they're theories, and why they are only studyable up into as models up until a certain point. And that point is hard to ascertain. So another way that we can describe physics is that physics is just math with units, where the fundamental, I had a professor who taught math methods for physicists, and he said that the most important thing about physics was that you could do unit analysis. You could figure out how something would change just by looking at the units, or how something would react by looking at the units of the variables that you're plugging into an equation. So units are physical quantities such as length, mass, time, electric current, temperature, amount of a substance, or luminous intensity, which are the 7 fundamental units laid out in the book, or combinations of those units such as length per time for speed, which are derived units. So length per time, so length has units of miles or meters or kilometers or a ton of different units. Time tends to be seconds, but it can also be hours or minutes. So we have derived those 7 fundamental units based on really specific pure or really specific quantities that we can measure in the real world. For example, the second is defined by being a number of rotations for a vibrating isotope. So a vibrating nuclear atom or nuclear isotope. And then the kilogram used to be, it's changed more recently to accommodate, to make these units more in line with each other, but it used to be that you just had 1 kilogram, which was like a metal, a cube of metal held in France that was defined to be equal to exactly 1 kilogram, and everything else was measured according to how much mass it had compared to that. But combinations of those units are called derived because you do not have that same amount of fundamental, so you cannot just measure a unit per a mile per hour without knowing what a mile is or knowing what a second or an hour is. So you have to derive it based on these fundamental units. And then the units that we use as scientists are called SI units. It's Le Système International de Units, or something like that. I don't speak French, but it is something similar to that. And it's used by most scientists and most people around the world. So kilograms, meters, and seconds are all SI units, whereas in America and the UK, they tend to use feet or miles for length rather than meters. And then another thing that you're going to see as you're reading through the book is that instead of writing numbers completely out, like 1,600,000 like we have there, we write them out as 1 digit, point however many digits are interesting or like are useful to the right of the first digit, times 10 to the number of value, or 10 to the n, where n is the number of well, basically just 10 to the nth power, so the number of decimal places over you are from 0. So for example, you have 1,600,000. That is going to be 1.6 times 10 to the 6, because there are 7 digits, but we only care about the digits past the first, or we try to simplify the digits past the first one. So we take 1, and then that 0.6, we could also have 1,652, and that would be 1.652 times 10 to the 6. But you just measure how many digits you are from the 0 spot, and that's how many 10 to the and then your scientific notation is 10 to that number for writing it out. And you can also use scientific prefixes or Greek prefixes to denote the magnitude. So 1,000 grams is equal to 1 times 10 to the third grams, because there's 1 1 and 3 zeros to the right of it. So it's 1 times 10 to the third. And what we've decided that means is that we have the units kilo, which means 1 times 10 to the third grams. So 1 kilogram is 1,000 grams. 1 centimeter is 1 times 10 to the negative 2 meters. So it's 1/100th of a meter. So that is just how you do that. That's something that is going to be something that you're going to use for practice, but it isn't. It's a good practice, but it isn't really the science. It is mostly bookkeeping. What does kind of end up being science, and the last thing that I'm going to talk about is precision versus accuracy. So you want a very precise and highly accurate model, but you're not going to be able to get that. So you're not going to be able to get it exactly on the value that you want, just because of impurities in your experimental method slash actual uncertainty that's baked into the laws of the universe with quantum mechanics. So what you're aiming for is high precision and high accuracy, where precision means that all of your data points are close together, and accuracy means that all of your data points are are centered around the main thing that you're looking for, the correct answer. So when you look at these bullseyes, you have a low precision, high accuracy bullseye on the left, which is centered around the center of the bullseye where you're trying to hit, but it isn't very close to, none of the hit pieces that hit are very close to the center. In the middle, you have a low accuracy, high precision, which is very close together. You were very good at hitting this one spot, but wasn't very close to the actual value that you were looking for. And then what you actually want is high precision, high accuracy. So this comes down to, this is like a fundamental thing that we get to understand with physics or with any science, that there is going to be uncertainty because of how you there is going to be uncertainty, there is going to be wiggle room because of how you set up the experiment, but you're going to try to eliminate that wiggle room and keep it in mind when you're testing your theories and hypotheses, that there could have been some inaccuracy that you didn't account for. So science is constantly changing. It's constantly building upon itself with this acknowledgement that you cannot always be perfectly right all the time. So that is all I have to say about physics, or what is physics. So I'm going to leave you to the homework this week. I'll try to get another lecture up over the weekend. And I hope to see you again soon. If you have any questions, please reach out to me over my email. I will try to answer all those questions as soon as possible. All right, thank you very much. See you later.